Well, hello. So I wanted to record this just to let you know about the test and how it was graded. So each problem on the test was worth 20 points except for the one where you had to just factor and the one you had to list the three requirements for continuity. Now, I'm not going to go through every problem on the test because for the most part you all kind of got the same problems incorrect. So just to point out some things, if you did not show that the function was indeterminate explicitly by showing 0 divided by 0 and how you got there, then you lost 5 points, so 5 out of 20 for the problems. I was fairly lax on the grading of some of your equations. You know that you want to include equal signs as you go from one step to the other. On problem number 2, you probably want to put parentheses around the numerator so that you can identify those better in terms of using FOIL to evaluate those. Number 4, 3 requirements for continuity. About half of you got that right. The requirements are that the function has to exist or is defined at some value of x equals c. The limit has to exist and the value of the function has to equal the limit. So those are the 3 requirements. The first one that people had problems with, most people had problems with, was number 6. So this was one of these trig problems. Again, you need, even the trig problems, you need to show that the result is indeterminate, just like you did with the other ones. And the cosine of 0 degrees or 0 radians is 1. And for the most part, we do use radians in evaluating the angles in calculus, not so much degrees. Anyway, we have 1 minus 2 cosine x plus cosine squared x all divided by 3x squared. So you needed to factor the numerator, and even though it has cosine in there, it's similar to having to factor something like this, except instead of x we have the cosine of x. So if you were to factor that, you probably would get it right, which is 1 minus x times 1 minus x. So when you multiply this out, you'll get 1, you get negative 2x, and you get positive x squared. So what you end up with is 1 minus cosine x, 1 minus cosine x, and you divide by 3x squared. So there were 2 squeeze theorems, and I just told you to evaluate this. So cosine of 0 is 1, so you get 1 minus 2 plus 1, so you get 0. And of course, 3 times 0 squared is 0, so you get an indeterminate result. So there are the 2 squeeze theorems. The limit as x goes to 0 of the sine of x over x is equal to 1, and the limit as x goes to 0 of 1 minus cosine x over x is equal to 0. So it's the second one that we use in this problem. So what we would do is we could take this 3, which is in the denominator, and put that out up front. Or you could say the limit of 1/3 is just 1/3, and then you'd have 2 things remaining. So you take the limit as x goes to 0 of 1 minus cosine x over x, and then you multiply that by the limit as x goes to 0 of 1 minus cosine x over x. And the squeeze theorem says both of those equals 0, so you should have had 1/3 times 0, which of course is 0. I think the biggest problem here was just a lot of you couldn't remember how to factor this, and Miss Pratt said you should have known how to do that, so I'll believe her. Okay. On number 7, so again, you plug in -6. So you always want to plug in what the value is, even when you have one-sided limits like this. And what you would have ended up with is 12 over 0. So it's not indeterminate, it's undefined, which means that we have to look at infinite limits. So I wanted to see that. You lost 5 points if you didn't show that explicitly. Now, what I did in this case, some of you didn't do it exactly this way, but I'm going to do it this way. So I'm going to factor the denominator. So if you factor the denominator, you'll get x plus 6 and x minus 5. So you can see at x equals -6, this goes to 0, and that's why you get a 0 here. So if we want to know which value to evaluate, so we draw this number line. Here's -6, so it's on the negative side of -6, so it's like -6.1. It's probably a good number to try. And so what I would do is I'd plug those in, except for these two I would just plug in -6, because I don't need to worry about this little tenth. It doesn't really affect everything. So you get 6 minus -6 in the numerator, and in the denominator you get this first term, which we'll come back to, and then you have -6.1 minus 5. Actually, just -6. We don't need to make it 6.1, just -6. And here we have -6.1 plus 6. So what you want to do is look at the sign of each one of these. So 6 plus 6 is 12, which is positive, so I don't even worry about what the number is. Just want to make sure it's positive or negative. And then down here, -6 minus 5 is obviously negative. And -6.1 plus 6, well, this is bigger than that, and it's negative, so this is going to be negative. So you have an even number of negatives, and so the answer, final answer, is -infinity. Positive infinity, sorry. You have an even number of negatives, so it should be positive, so you get positive infinity. And you can do the same kind of thing on problem number 9. Again, you should have gotten 13 over 0, I think. Number 9 is 13 over 0, which means that it's not going to exist, but we can evaluate the one-sided limits. So you do the same kind of thing as here, and you end up with -infinity. If you look at these terms, one thing is, no matter what x is here, you're going to get a positive quantity because you have something squared. So this is going to be positive because of the squared nature. This one is going to be 4 minus 9, which is negative. And here, if you put 4 in, you're going to have positive plus positive, so it's going to be positive. So we have one negative, so the answer is going to be -infinity. Okay, number 10, everybody seemed to do pretty good on that one. Number 11 was the next one that most people messed up. So, I was very clear about, if you don't approach 0 with one of these trig function limits, you just evaluate the function. So if you didn't just evaluate the function, you got penalized pretty heavily there. Now remember that so to evaluate it at that point, just plugging it in to see whether it's indeterminate. Well, it's not going to be indeterminate, but you could see whether it's indeterminate. I mean, it could still be indeterminate even if you're not going to 0. So you should have plugged it in anyway, just to see whether it's indeterminate or not, which you would find out it's not in this case. So what we're doing here, when you have the sine squared of x, it's really the sine of this thing squared. So that's how I'm going to do it. I'm just going to rewrite it as that. And then I just plug in x, so you get the sine of 3 times pi over 6 quantity squared divided by 3 times pi over 6 squared. So 3 pi over 6 is the same as pi over 2. So we get the sine of pi over 2, and we square that. In the denominator, I can go ahead and multiply this out. So I've got 3 times pi squared divided by 6 squared, which is 36. But the sine of pi over 2 is 1. So the numerator becomes 1. So we have 1 squared over 3 over 36. Well, we could simplify that. That's going to be pi squared over 12, or 12 divided by pi squared. And that's what I wrote down, but if you did it, it's like 1.2 something. So either one of these things was acceptable, and the more you got closer to just evaluating the function, the better you are, the better off you were. And Mr. McGee did a good job explaining the last problem. So you did better than my class. I didn't. I did talk about it in the review, but they didn't. That's the end of the review. So I think they tended to do that last. They didn't think about it enough. So the only things that I'm going to mention here is, I did say which of the discontinuities is removable, and some of you just said there's a hole, which is a removable discontinuity, but you didn't explicitly say it. So let's look at what we had. So you had, if you factored the numerator, you got this, and if you factored the denominator, you got that. So you can see I've got this common factor in the numerator and the denominator. So that means at x equals -2, I have a removable discontinuity, because it is a hole, but that's not sufficient. And you also have one here at x equals 3 when this goes to 0. In that case, it's a vertical asymptote, so I didn't ask you to call this a non-removable, but if you did, that was good. So that's a non-removable discontinuity. Now, as far as defining this function so that the discontinuity was removed, what you do is you take the limit as x approaches -2 of this original expression, but you can cancel out those, so use the dividing out technique. So you end up with x plus 7 over x minus 3, and you're not going to end up with anything indeterminate there, so you just plug in the numbers. So you get -2 plus 7 over -2 minus 3, which is 5, divided by -5, which is -1. So the way you define it is you're going to break it up into 4 intervals. So I'm going to show the function first, and except for the hole, you're just going to write the same function down here. So you usually start at -infinity. So we'll start at -infinity, and we're going to go to the smaller of these, more negative, which is -2, but not include -2. Then at x equals -2, normally the function would not exist there, but by saying that the value of the function f of x, so f of x in this case equals -1, this value at x equals -2, then you go from -2 to the non-removable discontinuity, and you write out the function again. And then finally you go from 3 to positive infinity. So the function is not defined at x equals 3. So you can't remove that out of there. So that's what you should have had. Some people didn't evaluate the function, they just showed this thing, which I guess theoretically is okay, but it's not what we discussed, or Mr. McGee discussed. Okay, so overall I'm happy. Hopefully you're okay with what you got. I mean, I think everybody did. At this point, everybody has the potential for getting an A or a B in the class, so just don't hesitate to ask if you need anything else clarified.